Hi everyone, welcome to this video. This is Mr. Kier, and we're going to be looking at a review of nomenclature, and then we're going to be looking at acids today. So I thought I'd start by quickly reviewing the summary sheet you already have. So on the right side, when we're dealing with any of these two nonmetals, what you have to be aware of is that you use prefixes. You do not cross over, you don't reduce, you go by the prefixes. Whatever they say, you go by it. If I've got ionic compounds over here, it's a metal and non-metal. You're going to be crossing over using the appropriate charge for the ion, and then you reduce if necessary. No prefixes are required. And for ionic compounds, you typically have binary compounds where you have the "ide" ending. Now, sometimes the metal involved with the ionic compound has more than one possible charge. They are the multivalent, and you're going to be using the Roman numerals to indicate the charge of these. You're going to have copper, zinc, tin, and lead. And you can also use the Latin method where us means the lower. So cuprous, for example, would be one positive, and ic is higher, so cupric would be the two positive version of copper. Then the other day we looked at polyatomic ions. These are clusters of atoms that act as a single ion. And we saw how we can use Nick the Camel, Crave, Clam for Supper at a Crosswalk in Phoenix to remember the charge and the formula for each of these. There are some new ones this year you did not see last year. For example, chromate, dichromate. We also know that chlorate has fluorate, bromate, and iodate, ions which are very, very similar. And carbonate is similar to silicate as well. Other ions we looked at were acetate. This is the unusual one that the metal goes last. Ammonium, which is positive, hydroxide. And the other thing that we saw yesterday was most of the time these polyatomics have an 8 ending. However, sometimes they can vary in the number of oxygens. So if they have an extra oxygen, we use the prefix per, so per 8. This would be percarbonate, for example, here. If we're missing an oxygen, we change the ending instead of 8 to ite. So for example, this would be sulfite over here. And we can also be missing two oxygens. When we miss two oxygens, we use the hypo and then the suffix ite. So we're going to do this. For example, sulfur here with two oxygens. Instead of sulfates missing two, it's going to be called hyposulfite. So that's it for the review. It's good to pause right now. And what we'll do is we're going to continue with acids in just a moment. Okay, we're back right now, and you can see here I've listed a variety of commonly seen acids. So we've got hydrochloric acid, sulfuric acid over here. I have carbonic acid and even acetic acid, you commonly know as vinegar. And you look at all of these acids, things that you notice right away is that instead of a metal, we have a positive hydrogen ion associated with each of these. So that's really what determines what an acid is. Remember in the acetate, the ion is at the end. The other thing you notice is when we have the acids, they typically have an ic ending. So these ic endings indicate an acid. Now, it's not enough just to have these compounds. What has to happen is these compounds have to go into water. So we have this AQ. This AQ means aqueous. And what it means is that the hydrogen chloride here goes into water and it breaks apart. It ionizes, we say. It's going to form ions. You're going to have positive hydrogen and a chlorine ion resulting from this. Let me just change this a little bit to make it look like it's breaking apart. There we go. That's a little bit better. So there's my hydrogen and my chlorine ion. Same thing's true over here. Here I'm going to have two hydrogens given off by this sulfuric acid, and you're going to have your sulfate ion. Here we're going to have similarly two hydrogens given off by the carbonic acid, and we're also going to have a carbonate ion being released. And finally, we're going to have our acetate ion and then our hydrogen ion. So the big thing here is that these acids in water ionize and they give off these hydrogens. And these hydrogens determine the acidity of a particular solution. The other thing is they also have the ic ending. So that's a quick summary of these. So let's look at a couple of examples. So the simplest acids are the binary acids. These are ones like hydrochloric acid, hydrosulfuric acid, hydrofluoric acid. They have two parts only. They're very, very simple. That's why they're called binary acids. So you have a hydrogen plus a nonmetal dissolved in water. That's very, very important. And what that gives you is this acid. And the way we name them is hydroic acid. So for example, hydrogen chloride in water is hydrochloric acid. Hydrogen sulfide, hydrosulfuric acid. And hydrogen fluoride would be hydrofluoric acid. You get the idea there. So in your workbook, you have this, and you should be copying this note down. Now remember, a binary acid has two elements associated with it. It has this naming format, hydro space ic acid, where the space here would represent the non-metal that's associated with the acid. And then the formula, again, is H blank AQ. The AQ means that you are dissolved. So very, very, very important. So let's look at a couple of these. So on this side, I'm going to be listing these various gases. These are the gases that dissolve in water to give you the acid. So for example, let me just change this. So what happens is for hydrogen chloride, it's a gas, you put it in water, it forms hydrochloric acid. And we put the HCl AQ. If you don't have the AQ, it's not an acid. Hydrogen bromide, here we go, hydrogen bromide. It's a gas. And when this dissolves, it's going to give hydrobromic acid. And the formula is the same formula. The only difference is you're going to have the AQ at the end. So very important that you have the AQ there. Let me just change that. Okay, now here I don't know the gas, but I can work backwards. So I've got my HI. So this would be hydroiodic acid. And it's coming from this hydrogen iodide gas that's dissolved in water. You get the idea. Okay, so it's relatively straightforward. Hydrofluoric acid would be HF. Remember the AQ at the end, that must be there to indicate it's an acid. Here's my hydrogen fluoride gas. And then over here we've got hydrogen sulfide. And it's going to be dissolved in water to give you hydrosulfuric acid. And this is going to give you H2S AQ. Okay. So I'm just going to add in a couple of last minute details here, but overall, this is the format for binary acids. Now, we can also have polyatomic acids that are associated with hydrogen. So let's look at some of these. So here I've got a hydrogen instead of a metal that's associated with these polyatomics. So when chloride has a hydrogen and it's dissolved in water, it's called chloric acid. A sulfate with hydrogen dissolved in water gives you sulfuric acid. And carbonate with hydrogen in water gives you carbonic acid. So the oxyacids, the naming is something ic acid. There's no hydro. Hydro, we only use that for simple binary acids. So this is the note that you have in your workbook. So I'd just like you to put this over here at the side. H plus polyatomic ion gives you oxyacid. And when you have this, it's space ic acid. So all of these. So for example, you might have this, a chromate ion associated with hydrogen. So this is chromic acid. What you have to remember though, that all of these really should have an AQ at the end, and that indicates that these have been dissolved in water. That's the proper way of doing this. So we should fix this in our workbook so it's properly done and we're consistent. So again, add AQ to each of these. Now, one last thing we have to do. Just like earlier, we had, remember we had the polyatomic ions had derivatives. So if they had an extra or missing set of oxygens, they had to change the name. So if I had phosphate, the extra oxygen would give you perphosphate, so PO5 instead of PO4. If I'm missing an oxygen, I'd have PO3, so phosphite. I use I to indicate one missing oxygen. And then if I'm missing 2 oxygen, I'd be using hypophosphate. Well, the same thing is possible with acids. I could have acids with 1 extra oxygen in the polyatomic or 1 missing oxygen in the polyatomic, or even 2 missing oxygens in the polyatomic. So these have a name as well. So the normal, the standard, instead of 8, we use ic for acids. This is phosphoric acid. Okay. Now, just like before, I put in per to indicate an extra oxygen, but instead of 8, per 8, I use per ic for the acid. So per phosphoric acid. With the polyatomic ions up here, if you're missing an oxygen, it's phosphite. Here, instead of phosphite, I use phosphorus. Us means smaller, so I have less oxygens here. And if I'm missing 2, instead of hypoite, I use hypous. So this would be hypophosphorus acid. So ic is more, us is less. And this is similar to what we did when we did the Latin method for naming multivalents. So here's the same thing, just another chart showing you the ic is the normal. Per ic, you have an extra oxygen. Us, you're missing an oxygen in the polyatomic. Hypous, you're missing 2 oxygens in the polyatomic. So if you want, you can pause and take a look at these. And basically, this is in your workbook. So it's the same system. So again, if you got an extra oxygen, it's per ic. The normal is ic. If you have less us, you have 2 less hypous. So try these out and see how you do. I'll pause right now. Okay, let's see how we did. So this one here, it's nitric acid, but we're missing an oxygen, so we use nitrous acid. So we should have acid at the end over here. So acid. Over here, sulfurous acid. Again, we're missing 1 oxygen, so this would be H2SO3. I forgot this one. Phosphoric, this is a regular one. Carbonic, H2CO3 would be regular. This one is regular, HNO3, nitric acid. Oh, here's a phosphate missing 2 oxygens. So this would be hypophosphorus acid. Us is less, don't forget. Per nitric acid. So you've got your nitrate, the hydrogen, and you've got the extra oxygen. Hypochromous, you're missing 2 oxygens, so instead of CrO4, you have CrO2. Charge is still 2. So that's about it. So just to quickly summarize, a binary acid, it's a hydroic acid. So for example, hydrochloric acid. Oxyacids, they have polyatomic ions with 8. The acid is ic when it's dissolved in water. So for example, chloric acid. If you've got fewer oxygens, instead of using ite, you use us for acids. And that'll be an example, be chlorite. Instead of chlorite, you do chlorous acid for acids. And that's it. So hopefully you picked up a thing or two from this video.